Hi, I'm Dr. Christopher Sutton, and welcome back to my Introduction to GIS video series. In this video, we will examine reference ellipsoids, which are mathematical models that approximate Earth's surface. Reference ellipsoids are used as a baseline for mapping, positioning, and geodetic calculations. Because Earth has an irregular shape with variations in topography, a smooth reference ellipsoid provides a practical means for computation and analysis. For a long time, it was generally believed that the Earth was perfectly spherical in shape. In the 1600s, Isaac Newton postulated that Earth is not spherical in shape because of gravitational forces and rotational forces. Specifically, he postulated that the axis between the poles would be shorter than the equatorial axis. Thus, Earth's shape would be an oblate spheroid, which is a special type of ellipsoid. An oblate spheroid is one of two special types of ellipsoid. In an oblate spheroid, the equatorial axis is longer than the polar axis. The prolate spheroid is the other type. In it, the polar axis is longer than the equatorial axis. In Earth geometry, the difference between the lengths of the polar and equatorial axes is mathematically described in terms of flattening. In geometry, flattening is a measure of how much an ellipsoid deviates from being a perfect sphere. Here we see the formula for flattening, where we take the equatorial radius and the polar radius. We subtract the polar radius from the equatorial radius and divide by the equatorial radius, which results in a ratio. Newton predicted an equatorial radius of 6,378 kilometers and a polar radius of 6,350 kilometers, which is 28 kilometers shorter than the equatorial radius. This results in a flattening ratio of 1 to 230. When used to describe Earth's shape, it is called polar flattening because the polar axis is shorter than the equatorial axis. In GIS, we use mathematical models of the planet called reference ellipsoids. Reference ellipsoids have a smooth, uninterrupted surface and integrate the flattening ratio. Many reference ellipsoids have been calculated since Newton. Why is this? Early ellipsoids were based on limited geodetic data, often derived from regional surveys or astronomical observations. As technologies advanced, more precise measurements of Earth's shape and size became possible. Newer ellipsoids were developed to incorporate these more accurate global measurements. Earth has regional variations in shape. Earth is not a perfect oblate spheroid. Its shape is irregular due to variations in gravity and topography. Early ellipsoids were often optimized for specific regions, leading to discrepancies when applied globally. There have been several scientific advancements that have been built into newer ellipsoids. For example, as our understanding of Earth's gravity field improved, new ellipsoids were developed to better approximate these features. In other instances, ellipsoids have been updated when technological advancements allowed for their recalculation. Also, with the rise of global navigation systems like GPS, there was a need for a single, globally consistent reference ellipsoid. Let's examine some reference ellipsoids that are commonly encountered in GIS. We'll begin with the Clark ellipsoid of 1866. The Clark ellipsoid is a ground-measured ellipsoid, meaning that Clark went to various places on the planet's surface, did measurements, and then used those measurements to calculate the ellipsoid. The Clark ellipsoid is the basis of the North American datum of 1927, which we will discuss in an upcoming video. The flattening ratio of the Clark ellipsoid is 1 to 294.9786982. The Hayford ellipsoid of 1909 is also a ground-measured ellipsoid. It was adopted internationally in the early 20th century and was the basis for the European datum of 1950. It has a flattening ratio of 1 to 297. The Geodetic Reference System of 1980, or GRS-80, was created using data from satellites. It is the basis for the North American datum of 1983. It has a flattening ratio of 1 to 298.257 222 101. It has remained relatively unchanged since its introduction. Finally, we have the World Geodetic System of 1984, or WGS-84. It should be noted that WGS-84 is a system with many components, one of which is the WGS-84 reference ellipsoid. The WGS-84 reference ellipsoid is the standard reference frame for GPS and most global applications. Its flattening ratio is 1 to 298.257 223563. In addition to being the ellipsoidal model for GPS, it has been updated several times to improve its accuracy for GPS. WGS-84 and GRS-80 ellipsoids use very similar parameters. You'll discover that the differences between GRS-80 and WGS-84 are typically so small that they don't affect most everyday applications. There are instances when the differences between the two do matter. For example, high-precision applications. Sometimes there is a need for sub-centimeter accuracy, and so choosing between the two reference ellipsoids matters. It also comes into play when transforming coordinates between datums based on the two ellipsoids. Reference ellipsoids are fundamental to accurate mapping in GIS. They provide a mathematical approximation of Earth's shape, ensuring precise coordinate systems. Choosing the right reference ellipsoid is key to reducing distortions in spatial data. Join me in the next video where we will discuss the geoid.